Good morning. Welcome to CSIR Net Foundation course. So, in this class, we are going to discuss uh, under group theory. We are going to discuss semi-group, and its uh, properties as well as some problems on CSIR Net. Let's see one by one. So, let's recall what is meant by group. A group nothing but a collection of well-defined elements in a set with the binary operation star which satisfies closure, associative, identity, inverse, and so on. Closure, associative, identity, inverse. If it satisfies by the elements in the set, then we say that non-empty set G is a group. And we have given several examples for that. In this class, we are going to define the semi-group and its related concept. Semi-group. So take G is a non-empty set with a binary composition, say star. So here G comma star is semi-group if A star B star C equal to A star B star C. For all A, B, C belongs to G. For all A, B, C belongs to G. So what is the relation between group and semi-group? So we can able to bring the note immediately. Since this is associative property in a group, so every group is a semi-group. But converse need not be true, because here it is only associative law, right? Again, we can give an example. So again, example is set of all natural number is a semi-group under multiplication. That is n comma product. It is a semi-group. But n comma product is not a group under multiplication. But n comma product is not a group under multiplication, because the inverse elements under product is not exist in the set of all natural numbers. That is the reason. So n comma product set of all natural number under multiplication is a semi-group but not a group. Okay, it is a semi-group but not a group. Okay, so there are several unique results. We'll recall one by one, right? Okay, so before going to recall further examples or concept, we'll see some few questions based on net or other exam problems. Question number 1. Let G be a finite group. Let G be a finite group and A equal to collection of all x belongs to G such that x squared is not equal to identity element. Similarly, B equal to collection of all x belongs to G such that x cube equal to E. Then option A, number of elements in A is E1. Option B, number of elements in A is odd. Option C, number of elements in B is even. Again, number of elements in B is odd. So how do we solve this? Here G is a finite group and A and B are defined like this. Then what is the cardinality of A? Whether it is a even or odd. Similarly, what is the cardinality of B? Whether it is a even or not. That is the question. Right? So how do we solve this? Here x belongs to G, but x squared is not equal to identity element. Right? So here G is a finite group, A and B. Okay. These are all subsets of G only. Here, if x squared not equal to E, if x squared not equal to E, so what are the possibilities? Just think. What are the possibilities? Just think whether there exists some k such that x power k equal to E. There exists some k such that x power k equal to E. So from this, we can able to give that x power minus 1, right? X power minus 1 power k equal to E power minus 1. Like x power minus 1 power k equal to E for all x belongs to G. Right? So thus x belongs to A if and only if x inverse belongs to A and x equal to x inverse and x equal to x inverse. Therefore, we have x1 comma x1 inverse, x2 comma x2 inverse. Similarly, xl comma xl inverse. Therefore, total number of elements equal to 2 times L. L may be even or odd. You will get only even. Therefore, number of elements in A is even. Number of elements in A is even. Right? Therefore, option 1 is number of elements in A is even. Okay. Again, you can able to conclude from either number of elements in B is even or odd. If you proceed like this, suppose X belongs to B such that X cube equal to E, right? X cube equal to E, we can able to bring it either X equal to E or X not equal to E, but X cube equal to E, right? So here X equal to X inverse. Here X is not equal to X inverse. Right? In the same manner, if you use the above argument for this, you will be getting number of elements in B is 2L plus 1, that is odd. 2L plus 1. Okay. So the correct answers are A is even and B is odd. Okay. Right? Right. So similar like this, we can able to prove a simple problems in by using a group theory. Next, net gate question. Suppose I am taking a group G equal to n by n matrices. Collection of all n by n such that A belongs to R star. R star nothing but R without 0. Right? So this is a set. Okay. Then G is a group under matrix multiplication. G is a group under G is a under matrix multiplication. This is true or false. This is the question. G is a n by n matrix for all A belongs to R star nothing but R without 0. Then G is a group under matrix multiplication. Under matrix multiplication. Verify its closure, associative, identity, inverse. Right? Whether these four conditions has been satisfied by A by G. In that case, this is true. Take it as a classwork and complete this. Next, we are going to start a new topic, which is order of a group. Order, right? If G is a group, so number of elements in a group is called order, right? Even more distinctly, number of distinct elements in a group is called order. So it is denoted by O of G, modulus of G, or like this. There are several notations. If order of G is less than infinity, then we can say that G is a finite group. So example for a finite group, maybe example z equal to zn u of n over zp, or examples of a finite group. Finite. Here we know that this is the order is n, and what is the order of u of n? Nothing but pi of n, right? Order of zn is again n, right? So what is the order of gln of zp, right? Pn minus p naught, Pn minus P1, so on so, Pn minus Pn minus 1, right? Okay. So similarly, we can define order of an element. Similarly, we can define order of an element. So suppose take a element A belongs to G, then order of A. For example, if A is an element in a group G, then order of A equal to n, then there exists some smallest integer n belongs to Z such that A power n equal to E. Right? That is, if there exists a least positive integer n such that A power n equal to E, then n is a order of an element. If no such positive integer exists, then we say that the order of A is infinite. No such n exists, then order of A is infinite. Order of A is infinite. Okay, so here what is meant by order of a group, order of an element, and other things we have discussed. Similarly, we can in the order itself we can able to bring some problems. We will discuss it in the subsequent topics. Next, subgroup. So what is mean by subgroup? Suppose G is a non-empty set, which is a group. H is a subset of G. If H is said to be subgroup of G, if H itself a group under the operation defined on G, under the binary operation defined on G. Okay. Simply we denote it as H is a subgroup of G, or H is a subgroup of G. Right? So we'll take example G equal to a set of all integers. Then H is equal to 2Z. Yes, here 2Z is a subset of Z, right? And it satisfies all the conditions for a group. Therefore, in general, we can make it as a another NZ. Right? So H equal to N times Z. Therefore, NZ is a subgroup of Z. Similarly, we can have another example also. Suppose I am taking an example 1 minus 1, I minus I. Subset is 1 comma minus 1. So here H is a subgroup of G. Right? And the easiest result to prove a group is subgroup. It is a finite subgroup test. It is a finite subgroup test. If H is a non-empty set, which is a subset of G, right? Then H is a subgroup of G if and only if H is closed. If and only if H is closed. That is, for every element A belongs to A comma B, B belongs to H, A dot B belongs to H. Right? This is one. Maybe we have another one-step subgroup test. Here, for every element A comma B belongs to H, then if A star B inverse belongs to H, then it is a subgroup of G. Then H is a subgroup of G. And from this, in the subgroup, we can able to see, suppose I am taking intersection of two subgroups is also a subgroup of G, and union of two subgroups is need not be a subgroup. Right? Intersection of two, the union of two subgroup need not be a subgroup of G. Suppose we can take an example. Suppose G equal to set of all integer under addition. Here H equal to collection of all -4, -2, 0, 2, 4, like this. And I'm taking another subgroup as K, which is -6, -3, 0, 3, 6, so and so. Right? We can able to see that H is a subset of G, K is a subset of G. So I'm going to make as a union -6, -4, -3, -2, 0, right? Again 2, 3, 4, 6. Now we need to prove that H union K is a subgroup, which is again another group. For every two elements, the sum of two elements belongs to the set. That is a closure property. Suppose I am taking 2 and 3. I am adding this, you will get 5. But 5 is not in the set. Right? 5 is not in the union. Therefore, H union K is right. So H union K is a subgroup. H union K is a not a subgroup. So we have taken a counter example to show that what are the things to be a subgroup, and you can take some exercises. Show that H equal to Nx such that X belongs to Z, set of all integers is a subgroup of set of all integer plus, right? And the second one, suppose every subgroup of an abelian group is abelian. Prove it. So we haven't discussed about abelian group. So we have already discussed what is in by group. So here it is a commutative law. Suppose if A comma B belongs to G, then A star B equal to B star A for all A comma B belongs to G, right? Then this is the law of commutative. If a group G satisfies commutative law, is called abelian group. Is called abelian group. So here I'll give an exercise, because in the first class we have discussed several groups. You go and verify whether the groups are again a abelian group or not. Okay, abelian group or not. Very simple as well as trivial examples are there. So you go and verify it based on the given definitions, simply you can verify whether this condition is satisfied or not. Simply, right? Okay. So in the next class, we are going to verify, we are going to define some problems on semi-group and um, what and cyclic groups. So before that, we will see a couple of definitions. Normalizer. If G is a group which is non-empty, here n of A equal to collection of all X belongs to G such that XA equal to AX is a subgroup of G, and this subgroup is called normalizer of a group G Similarly, we can able to prove center of a group. We can able to see what is meant by center of a group. Suppose take a non-empty set G, which is a group. If G is a group, right? Here, collection of all Z equal to collection of all Z belongs to G, such that XZ equal to ZX equal to XZ, right? For all X belongs to G is called center of a group, right? Center of a group is roughly denoted as Z of G. Again, you can prove that normalizer is a subgroup of G and centralizer is a subgroup of G, and G is abelian, then center of a group is equal to group. Center of a group if is equal to group. So here normalizer is for an element. Normalizer of an element. Center is for group. Okay. Center is for a group. This is the major difference. Here we can able to define centralizer. Centralizer, suppose if A belongs to G, then centralizer of A is denoted by C of A equal to collection of all X belongs to G such that xa equal to ax. Again, you can see that centralizer of an element is a subgroup of G. Is a subgroup of G. Centralizer, center, normalizer, all are a subgroup of a G. Right? Okay. So next thing we will be discussing about dihedral group in the next class. So till now we have discussed what is mean by semi-group and several examples based on a semi-group and some of the problem examples which are not an semi-group like this, right? So here I can give some of the problems based on abelian group. You can work out. If G is an non-abelian, if G is a non-abelian, then H equal to X belongs to G such that X squared equal to E is a subgroup of G. True or false? Right? Question number 4. If G is an abelian group, and H equal to collection of all X belongs to G such that order of X is finite, then H is a then we can able to see that H is a subgroup or not. So here simply you can check that simply verify. We'll discuss the rest of notions like dihedral group, cyclic group, and permutation in the next class.